Welcome to Ask and Learn.
For problem 20-11, just like the problem before it, 20-10, we have an electric fan blade rotating around a swivel support system. The swivel support system is fixed in the XY frame. The fan blade is in a series of rotating frames. It rotates about the vertical Z-axis. It also rotates about the horizontal x-axis, and then the fan blade itself rotates about an axis that is inclined 45 degrees with respect to the y-axis. The fan swivels about the vertical axis at a rate of 1 radian per second. It is accelerating it has an angular velocity about the x-axis at a rate of 2 radians per second. And the fan itself rotates about what I'm calling the s-axis, the spin axis, at 60 radians per second. Just as in problem 20-10, we're asked to determine the angular velocity and the angular acceleration of the fan blade. So first, we will find the angular velocity. That's going to be vector omega, and it's going to be the sum of two angular velocity components, vector omega z. The sum of three angular velocity components, vector omega z plus vector omega x plus vector omega z. Each of those correspond to the axes that I just described above. For this problem, we now have the addition of another rotation about the x-axis. The magnitude of the angular velocity is given in the problem of 2 radians per second. Now we need to figure out the direction of the angular velocity vector given the direction of rotation. For the right-handed rule, we're going to use the right-handed rule to determine that the counterclockwise rotation about the x-axis has a corresponding angular velocity vector that points along the positive x-axis. So for our vector component here, for the vector omega x, we have 2 times unit vector I radians per second, and that value is positive. It's pointing in the positive x direction. From the previous problem, 20-10, we know that the sum of the other two components, that is vector omega z plus vector omega s, that sum is equal to 42.4 unit vector j plus 43.4 unit vector k. Adding that to our x component, we get the complete angular velocity for the system. That's going to be vector omega equals 2 unit vector I plus 42.4 unit vector j plus 43.4 unit vector k. All of those components have units of radians per second. The next part of our problem, we're asked to find the angular acceleration. The book likes to use the notation vector alpha for that. I prefer to use the time rate change of the angular velocity, vector omega dot, and that vector omega dot is combination of vector omega dot for each of the 3 rotation axes that is given in this problem. For the first contributor to the total angular acceleration, we have the time rate change of the angular velocity about the spin axis. We can choose a reference frame for which that angular velocity, omega s, stays in constant direction. For that, the frame vector capital Omega equals vector omega sub z plus vector omega sub x will satisfy that criterion. We're also given that the fan blade is the angular velocity magnitude of the fan blade in that rotation, in that frame, that is, does not change with time. It stays constant. So we can assign this instantaneous change in the angular velocity of the spin axis to vector 0. And plugging that into the coordinate frame rotation transformation equation, we are left with, for the time rate change of vector omega s sub s, 0 vector plus the sum of vector omega z plus vector omega x, that sum crossed with vector omega s. That will give us the time rate change of the angular velocity of our spin axis component. Inserting those into the cross product matrix determinant operation, we are left with vector omega s time rate change equals negative 42.4 unit vector I minus 84.86 unit vector j plus 84.86 unit vector k. Those components have units of radians per second per second. For the next component of our angular acceleration, we have the time rate change of vector omega x that corresponds to the rotation along with the axis along the x dimension. For this, if we choose the rotation frame, capital omega equals vector omega z, that frame will satisfy our condition that the angular velocity in the x component does not change direction. That direction stays constant, rather. We also know that there is no time rate change of the magnitude of the angular velocity in the x direction. That can be set to 0 for our first part of our coordinate frame transformation equation. As such, for this component, the time rate change of vector omega x, what we're left with is this second component of our chosen rotating frame with respect to the fixed frame. That leaves us a cross product of vector omega z cross vector omega x. Inserting the cross product into our matrix determinant operator, we are left with 2 unit vector j radians per second per second. So we've satisfied 2 of our 3 contributors to the total angular acceleration. All that's left is to find the time rate change of the angular velocity along the vertical direction. Conveniently, we'll notice that for this component, this angular velocity its direction stays fixed in the fixed reference frame. So that we know that our capital omega vector we can set equal to 0, and we also know that that frame is rotating about the z-axis with a constant angular velocity in terms of magnitude. So its time rate changes 0. With those 2 terms of our transformation equation summing to 0, we're left with the time rate change of vector omega z equals 0. We have figured out the 3 contributing contributors to our total angular acceleration. All we have to do now is add them together, the result of which is vector alpha equals negative 42.4 unit vector I minus 82.9 unit vector j plus 84.9 unit vector k. Those components have units of radians per second per second. And that concludes our problem.